Something caused the extinction of the dinosaurs, or at least most of them. The birds represent a branch that made it through, but the giants of the dinosaur age, the tyrannosaurs, sauropods, and many other past species that fire the imagination, did not make it through. And their end in many cases came very abruptly, geologically speaking, though in truth, the dinosaurs as they were during their last days were in decline regardless, very likely due to increased volcanism. But extinction is a complicated process. While some species, conceivably, might have been instantly driven to extinction through vaporization by the asteroid if they were native to an area near the impact, and a great many others would have died off quickly due to the immediate and inescapable climate change. Other smaller dinosaurs, however, may have persisted for a significantly long time after the impact, but ultimately could not cope with a changed, but mostly recovered, planet. But the demise of the dinosaurs was a great mystery within science for many years. Why are there no large dinosaurs still walking the Earth? We find their fossilized bones, but not them. Again, other than the birds. But the birds are clearly linked to the dinosaurs in the same way that a cat is linked to a lion. They are related, both in their genetics, but more importantly their bone structures and physical appearance and their behavior. The birds, and indeed animal behavior overall, gives us clues on what the dinosaurs were like, at least broadly. But why did the birds survive and not the tyrannosaurs? It may simply have been size and mobility, but as to the cause, growing evidence suggests strongly that an asteroid impact was to blame. The most compelling evidence for this comes in the form of the so-called KT or KPG boundary. This used to be called the Cretaceous-Tertiary boundary, but in more modern times, it's most typically termed the Cretaceous-Paleogene boundary, dating to around 66.043 million years ago according to the most recent dating. This geologic feature is seen all over the world in rock of this time frame, and was first identified by a team of scientists in 1980, led by Nobel laureate Luis Alvarez. This strange thin layer of rock shows unusual, even mysterious, amounts of the element iridium, hundreds of times higher than the level should be for a layer of Earth rock. Iridium is an extremely dense metal that's very rare on Earth, but not particularly so in space, and indeed is an extremely useful metal here on Earth, in that it has a very high melting point that allows you to make crucibles for use in working with other metals with very high melting points. This is also useful in a more mundane capacity. Spark plugs sometimes use iridium tips because of the high temperatures involved, and we are likely to make use of iridium someday in space, both for its properties and its availability. But here on Earth, it's a very rare metal, so to see a concentration of it in sedimentary rock is basically unheard of, other than this particular boundary line in the geologic record. At the time, this was interesting, but it wasn't enough to nail down what actually happened. It was known that an extinction event happened about this time, and it was a particularly bad one, wiping out not just the dinosaurs, but 75% of all plant and animal species existing at the time. It was also known that the most likely origin for the iridium layer was space, suggesting pretty strongly that an asteroid had hit, but what was missing was a smoking gun, specifically meaning a crater. Craters on Earth are geologically transient features. This planet has been hit by objects as much as, say, the Moon. In fact, early Earth might have had it a bit harder than most planets in the solar system, in that it was smacked by a Mars-sized object that blasted off the material that would eventually form the Moon. But modern Earth shows very little cratering of meteoritic origin. And the ones it does show, such as Barringer Crater in Arizona, are so because they are relatively recent impacts, with Barringer Crater having hit within human prehistory, an estimated 50,000 years ago. This is a good example of how cratering on Earth weathers away rapidly over geologic time. While still quite impressive, Barringer Crater has weathered in the form of adding about 100 feet of sediment to the crater floor since the impact. Further, the crater rim has lost about 50 feet in height. Over geologic time periods, all visible traces of this crater will disappear, but it will remain detectable in the local geology for far longer, and this was how the great buried crater that marked the extinction of the dinosaurs was discovered. Known as Chicxulub Crater, This crater partly underlies the Yucatan Peninsula of Mexico. This crater is indeed the missing smoking gun. The evidence for it is substantial, including a gravity anomaly coinciding with the crater, shocked quartz from the impact, and also the presence of a somewhat mysterious telltale impact glass known as a tektite. This crater is also unique in that the very peak of its rim is still accessible to geologists, and dating the crater's formation coincides precisely with the K-PG boundary. Here it seems appropriate to make a comparison between Barringer Crater and Chicxulub. Barringer Crater was created during the Pleistocene period, in a time when Earth's climate was markedly different from today. This was the world of the mammoths, and this impactor did not cause any kind of mass extinction. Still, it must have been a sight to behold. The iron meteorite that formed it is thought to have originally been about 50 meters in diameter, traveling at a whopping 12.8 kilometers a second, or 29,000 miles per hour. When it hit, the resulting explosion was equivalent to about 10 megatons of TNT, far larger than most, but not all, nuclear bomb detonations on Earth. And here's where it gets strange. Something on the order of half of the impactor completely vaporized, resulting in droplets of iron rain falling out of the sky and onto the surrounding plain. As bad as that sounds, Chicxulub was far, far worse. Here the impactor is thought to have been as large as 15 kilometers in diameter and dug out a crater over 150 kilometers in diameter, or just under 100 miles. It also managed to pick a really bad spot to hit, right on the coast, which would have not only created the massive dust cloud that heralded the mass extinction, but also gigantic tsunamis. Evidence of these titanic tsunamis still exists in areas of the modern Caribbean in two forms. One is seabed sand where it's not supposed to be, deposited on what was then dry land, but also certain rocks and even the remains of land plants deposited in marine sediments where they are also not supposed to be. The excavated dust also happened to be of amongst the worst possible compositions. The seafloor was composed of gypsum sediments that when it hit would have released sulfur trioxide, which would then produce sulfuric acid when in contact with water, which much water was also vaporized at this time. This actually would have made the resultant dimming of the sun even worse than it would have been with normal dust alone. Several days after the impact, this material would have resulted in horrific acid rainfalls, which would have really driven the mass extinction, as a great amount of life on this world was poisoned. And here we come up against the notion of an impact winter, one of the worst things that can and has happened to this world at the hands of the solar system. And while we don't know all of the exact conditions of the aftermath of the Cretaceous-Paleogene impact, there has been some thought put into what would happen if such a thing were to occur now, and what we could do to avoid it. The concept is known as an impact winter, and hypothesizes the after effects of an impact in modern times. Now, meteorites, which are just tiny asteroids, fall to Earth constantly. Every day, a several-meter chunk of rock falls to Earth, and numerous new meteorites are identified every year. As an aside, the issue of meteorites is one where the scientific consensus lagged somewhat and ended up being proven wrong. Meteorite falls have been known for thousands of years. In the ancient Greco-Roman world, stones falling from the sky were often seen in a religious context, and were often enshrined in temples and associated with gods. But by the age of the Enlightenment, meteorites were seen with a somewhat dubious eye. Indeed, Thomas Jefferson didn't believe that stones could fall from the sky at all, and famously said it was more likely that the French scientists studying such rocks were lying. Fast forward a century, and things were not that much better. Meteorites were recognized as being rocks from space, but the consensus at the time was that they were so rare that it would be a complete waste of time looking for them. This changed when a self-taught meteorite enthusiast by the name of H.H. Neininger didn't buy it and started looking for them. Over the decades, he amassed one of the largest meteorite collections in the world for its time, and identified many new falls, showing that the consensus was wrong. Meteorites are not rare, and you can buy examples inexpensively these days. Moreover, we know that certain areas, such as parts of Antarctica, can actually deposit meteorites that have fallen on glaciers over centuries all in one spot for easy collection by scientists. So much for past consensus. Thankfully, the larger the rock, the rarer it is, and truly large asteroids that could deal severe damage to this world are very rare. Other natural disasters on this planet are far more frequent, such as wildfires, floods, and so on, but few have the destructive power of an asteroid or comet. But again, this depends on size. The good news here is that such impacts on average only happen about once every 100 million years. And since the dinosaur extinction event happened 66 million years ago, in a sense, we are not overdue for another anytime soon, at least on average. Looking at the impact that killed the dinosaurs, the power of that asteroid impact was staggering. 100 million megatons is the current estimate, making it 6 billion times more powerful than the Hiroshima atomic bomb, and dwarfs the power of all the weapons arsenals the world over, including nuclear weapons. And an object of this size, estimates range around 10 kilometers, doesn't even care about the ocean should it hit over water. It will just plow right through it, and into the bedrock below, lofting as much dust into the air as if it happened on land, but with more water vapor. Most meteorites, and thus most asteroids, would tend to hit over water due to the enormous amounts of the surface of the Earth being covered in ocean, but this is no advantage. The composition of the asteroid also matters here as well as size. An iron-rich asteroid is going to hold together better than a loose conglomeration of rock or ice. This really depends on what the impactor is and where it's from. Near-Earth asteroids represent the most common threat, and those can be iron-rich, but it's also possible for comets to hit, in which case it's more rocky and icy in nature. Though comet impacts are going to be rarer events, but they do somewhat change the equation. And now to the effects of a large impact if it were to happen today. The first thing is that anything near the impact would be vaporized. Then the lofted dust in the atmosphere would almost immediately start blocking sunlight. This in turn would lead to a massive drop in global temperatures to catastrophic levels. In less than a month, the world could see a drop in temperature on the order of over 10 degrees Celsius. As with the end Cretaceous impact, depending on the subsurface strata where the impact occurred, there may be a period of acid rain that would immediately kickstart the following mass extinction, specifically by devastating the plant life. But that's only the beginning. Over the ensuing first year, while global temperatures will recover to an extent, it would be many years before anything close to normal would be seen. This would kick off a kind of new ice age, though not for the same reasons as Earth's past ice ages. But that assumes that the impactor hits relatively shallow water. If it were large enough and hit deep water, the exact opposite could occur, where enough CO2 and water vapor is injected into the atmosphere to cause a severe greenhouse effect that raises temperatures rather than lowers them. And it gets worse. If the impact is really powerful, it's thought that it's possible that with enough energy, the impactor could damage the opposite side of the planet from it as the sheer energy telescopes through the planet. This could cause a huge volcanic zone to develop, which can in itself create a volcanic winter, and make the impact winter that much worse. And then comes the after effects and continued extinctions. The first thing might actually qualify as a biosignature if an alien civilization happens to be watching Earth when this kind of thing happens. The cold, the acid rain, and firestorms that seem likely to result from some impacts would cause a mass death of plant life on Earth, and in the firestorms, animal life. This could release a large amount of methane into the atmosphere as everything decomposes, the rise of which is in principle detectable at a distance. That much death and the resulting effects on the atmosphere could make the global situation even worse, even so far as to release enough material into the atmosphere to increase Earth's albedo through higher amounts of clouds, which will compound the cooling if that's occurring, and also make the resulting ice age of sorts that much worse. Again, depending on just where the asteroid hit, it could create gigantic oceanic megatsunamis that could devastate coastal areas and very far inland. If the end Cretaceous event were repeated, this would see on the order of 3/4 of all large species of life on Earth go extinct. And while even an asteroid cannot cause the extinction of all life on Earth, the microbes are too resilient, and only the sun, eventually cooking Earth, can wipe them out, it can definitely cause our own extinction. But before that happened would come the end of our civilization. Almost overnight, agriculture would cease due to the changes in the atmosphere and the blocking of sunlight. The effects would be catastrophic for the global human population and last at the very least a year, and not very many countries on Earth have enough of a stockpile of preserved food to withstand this period without massive loss of life. The other question is, as recovery happens, and assuming we aren't outright driven to extinction, how do we restart civilization? The first thing to note here is that we have some pretty serious technology these days. We can create artificial sunlight and grow food with it. We can also build things like underground seed banks to preserve our agricultural crops, and even restart forests if we had to. And studies of areas devastated by volcanic events show that even utter destruction, as what happened at Mount St. Helens in 1980, showed that life rebounds, and while it takes many decades for forests to recover, the process is indeed underway there. We can, in principle, restart civilization, but we'd also need to relearn a lot of lost skills that few these days can still do, such as manual agriculture without chemicals or equipment. However, human civilization may prove more resilient than one might think to such an enormous disaster, and there is hope here for restarting Earth's biosphere and possibly even almost entirely restoring it after such a disaster, including employing extinction mitigation efforts, including our own, above and beyond making ourselves a multiplanetary species with a group surviving on Mars. As an aside, there actually are species on Earth that, had we not been present, might have gone extinct after the last ice age. We have both caused extinctions, but we have also prevented them. A really noteworthy example is the avocado. This tree was adapted to the very same megafauna eating and spreading its seeds that would have been present around Barringer Crater when that impact happened. Without mammoths and ground sloths eating the avocados, the tree would have lost its niche and met a slow extinction through no transport of its seeds. But it didn't, and the reason may well be that right at the time when the megafauna disappeared, humans appeared in the avocado's native habitat of Central America, and we may have kept that tree from extinction. And then there is the vampire bat. It too lost its niche in the same area under similar circumstances. It had no megafauna on which to feed, except we appeared, and it's thought plausible that after the last ice age, we might have been a major food source for these bats. And still would be, except the Spanish-populated Central and South America with a smorgasbord of domesticated animals from Europe, which are now a major food source for the bats, and, occasionally, humans still are too. And I'm glad they survived, helped along by humans or not. Vampire bats are fascinating creatures with complex social skills within their groups, and avocados are delicious. But the point is, we manipulate our food and can intentionally, or even unintentionally, keep a species from going extinct. There are cases where the natural precursors of our food before selective breeding are now extinct. And with the advent of DNA technology and preservation, this intervention only becomes more doable. In fact, the concept of de-extinction promises to allow us to reverse past extinctions, or even genetically modify crops to more easily handle the effects of asteroid impacts. But there is a better way to do it. We basically have gotten lucky enough to survive to a point where our technology is now sufficiently advanced to detect dangerous asteroids, and in just a few decades avert our destruction by deflecting them away from Earth. This is an ongoing effort to develop that sort of technology, and now that the alarm has been raised, significant research is being invested in doing something about the problem. As time goes on, this may actually evolve from deflecting dangerous asteroids and comets to outright mining them completely away for their raw materials before they get anywhere near Earth. But here, a different set of questions could be asked. One can wonder what might have happened if the dinosaurs hadn't met a mass extinction event. Might they have continued their already ongoing decline, and most went extinct anyway? Or might they have found a new path and still dominate the Earth in some form? Could intelligent dinosaurs have resulted, and this planet might have had a technological civilization long before us? Would that have prevented our own evolution to intelligence from our own precursors that survived the extinction of the dinosaurs? Let me know what you think in the description below. Thanks for listening. I'm futurist and science fiction author John Michael Godier, currently worried about asteroid life. Remember, the asteroid series is on the list of ice shell objects that may harbor subsurface liquid water and possibly life. At least until a probe or even a car from Earth smacks into it and causes a mass extinction. Not good, and be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular, in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.